And with that, good morning everybody. Welcome back to Hillsdale and welcome back to Cal 2. Hope you all had a good break. Hope you all had a chance to relax up a little bit and enjoy life before we get back into the thick of things. Plan for today, we're going to start talking about Standard 9, Surfaces of Revolution, where we're going to be taking curves. We're going to be doing some spinning. And we're going to see what sort of surface area we can get when we try and spin curves to get various types of shapes. Shapes. I don't know why I said shapes weirdly. Got my usual office hours over the next few days, 11 to noon and from 1 to 2. As per popular vote, we're going to have a quiz Wednesday over Standard 8. If you remember, that's the arc length standard, so could have had it today. You all chose not to. So be it. Just as a heads up, I expect to do a Standard 9 quiz on Friday. We'll probably finish Standard 9. I'm planning on Standard 9 taking us through the end of class on Wednesday. And then once we get through Standard 9, then we are really going to change gears and start talking about some sequences and series. It's going to be fun. Wipe that frown off your face. Also, don't forget there's a web work assignment that is due tonight, homework 12. And that's still leftover stuff from looking at arc length. And I also just posted another one this morning, which will be due on Friday night, homework 13, which is over Standard 9 stuff we'll be doing today. So yeah, everything that could happen to me did happen to me over break, so I didn't actually grade any of the retests you all did from right before the break. My apologies. I'll get those back to you by Wednesday. Well, I can see you again before Wednesday, so I'll get those back to you on Wednesday. Yeah. Anybody have any questions or comments before we get started for today? What do you call an angle that's been in an accident? You call it a rectangle. Okay, and with that, we're going to jump into Standard 9. So let's see. So, here's the scoop. If you all think back to 500 years ago, before spring break, we talked about the idea of, given some curve in the plane, how can we find the length of that curve? Where even if we had something that's wibbly wobbly, it has some distinct curve to it going around, the idea was we would tug on the ends to stretch it out, find the length of that line segment. And what we're going to do today is related to that, sort of looking at another application of the different integration techniques that we've talked about. But instead, the idea here is we're going to be doing something three-dimensional today. So we're going to take some function, f of x, from x equals a to x equals b. And what we're going to do is we're going to do something we haven't done before. We're going to jump into the third dimension here. We're going to take our curve and we're going to spin it in a circle around the x-axis. So what the net effect's going to be is we're going to end up with a three-dimensional surface that looks something like this. Draw this little arrow here just to show how we've rotated. We've taken our curve, we've rotated around the x-axis. And what you sort of get if you turn your head 90 degrees this way is sort of going to be what looks like almost a vase sort of shape to it, in which we kind of have a top of our vase, we have a bottom of our vase. If we pick any point on the curve, we could sort of see like we have a circular cross section around the x-axis. And our goal for today is, given this sort of three-dimensional shape, found by spinning or rotating a function f of x around the x-axis. What is the surface area we are going to get of the resulting shape? So, to me, this is an interesting sort of question because this is a three-dimensional question. When you're looking at a three-dimensional object, it's trying to think about what's its surface area going to be. Everything we've done in this class so far to this point has been two-dimensional. So, time for a sneak peek of the inner workings of the college. The schedule of classes for next semester is scheduled, I believe, to come out this Friday. Once it does, I'm going to talk about what sort of classes kind of make for natural math follow-up courses to Calc 2, for those of you who are interested in going on in math. But the next, one of the next courses I would recommend for you all, if you're interested in going on from Calc 2, is to go on to, well, Calc 3, or multivariable calculus. And in multivariable calculus is all about what happens if you take ideas from Calc 1 and Calc 2 and move them into 3 dimensions or higher dimensions. And it's super important, by the way, for anyone who's interested in studying math or physics, or even econ. I'll talk more about that on Friday. This is kind of going to be our foray into 3-dimensional mathematics in this course. It's going to be in Standard 9. Any questions or comments before we start trying to find a formula for this thing? So, how on earth do we find surface area? Well, let's think back to the initial question from Calc 1 of, here's a curve from A to B. How do you find the area under this curve? My elbow. Ouch. Yeah, laugh at other people's pain, Jonah. You monster. If we had a function f of x from x equals a to x equals b, what's our general Calc 1 strategy for finding the area that's just underneath that curve? It's sort of a two-dimensional area problem, Bethany.
So we could take the integral of f of x from a to b.
Yeah, we would take the integral from a to b of our function. The definite integral specifically. What do we do when we evaluate a definite integral? Like, what's involved in taking a definite integral of f of x from a to b? Do we take f of x and we, I don't know, flip it upside down so it looks something like like that. Like, what do we do? Okay.
Find the antiderivative of f of x, and then take the antiderivative, that'd be minus the antiderivative of f.
Oh, okay. So you're trying to do the cheating method using the fundamental theorem of calculus, where we find an antiderivative, plug in our endpoints, and subtract it, and bada boom, that's what you get. All right. Let's say all right. How did we approximate this area though? Because as we've seen a lot of functions, it's difficult to find what an antiderivative might be. James?
Shove a bunch of rectangles under it.
Yeah, we shoved a bunch of rectangles under it. Essentially what the idea is we take a bunch of tiny little rectangles, this would be like a right endpoint approximation. We say, well, finding areas of weird abstract shapes is hard, but we know how to find the area of a rectangle. That's just base times height. So our idea was split up the region into a bunch of little rectangles and add up the area of the rectangles. And then as the number of rectangles you have goes to infinity, then this ends up giving you the same thing as Yes gave what the fundamental theorem of calculus would say. So my question is, how can we apply a similar sort of process over here in order to find the surface area of this weird three-dimensional shape? James, any ideas?
Maybe take a bunch of cylinders.
Take a bunch of cylinders. Ooh,
Yeah.
okay, and do what with them?
So sort of if you like flip the shape 90 degrees and then imagine.
Okay, so we've got like a cylinder going this way.
Yeah.
Okay, and then adding up the surface area of all of those cylinders.
Well, just the outside one.
The
It
out-
seems like not the.
what do you mean by the outside one?
The like the part that's a circle, not the circle on top or the circle on bottom, like the sort of stretch, the curved rectangle in the middle.
The curved rectangle in the middle. Okay, I see. Oh, you're saying
Yeah.
not like the two, like the top and bottom of the cylinder, but
Yeah.
just the side.
Yeah.
Okay, gotcha. Yeah, sorry, I wasn't sure what you were trying to say there first. Okay.
I suppose that you're rotating it full 360, you could do the integral times 2 pi.
Ah, yeah, 2 pi is going to get involved in there. Why 2 pi?
Because you're rotating it completely 360 degrees around.
And when you think 360 degrees, that's 2 pi radians, so 2 pi is probably going to get involved somewhere along the way. I agree. So James, I don't think we actually need to get something quite as complicated as adding up the surface area of a bunch of different cylinders. Technically, that's what we're sort of doing. But instead, what I'm going to do is I'm going to add up the area of a bunch of circles. Because if we think about it, if we take any point on our curve, and we rotate it 360 degrees around the x-axis, is going to give us a circle from taking that single point and just rotating it around. And the idea is if we add up the circumferences, or the perimeters, however you want to think about it, of all of these different circles, the perimeter of this circle plus the perimeter of that circle plus that circle plus that circle plus that circle plus every other the circle found at every other point on our curve, we can sort of think about how we would get the entire surface area of our shape by just adding up the perimeters of these infinitely many circles found by rotating around our function around the curve at each point. So our idea is going to be to add up the surface area the, not surface, circumferences of all the circles found by doing our rotation. So let's look at a single one of these points. This picture's getting a little bit busy, so let's maybe put another one over here. This will be our A, this will be our B, and if we rotate, we'll get a shape that looks something like this. If we were to pick a single point, like let's say at X in between, so this is our function f of X. So the dotted circle, so this dotted line, think of this as sort of going back around the back side of the surface, whereas the solid line is going around the front. One thing you'll learn if you go into deeper mathematics, trying to draw three-dimensional surfaces on a two-dimensional, say, chalkboard, it's kind of hard. It's not something I've ever perfected. But the purpose of the dotted line is usually to say we're going around the back side, whereas the solid line is going around the front side. Yeah, Phoebe?
Is that picture meant to look like that one, or is it supposed to look different?
It's meant to look something like the other one.
Okay, well, just because like the bottom curve is like mirrored.
Oh, all right, let me try this again. Oh yeah, because no, this isn't supposed to. Okay, so it's supposed to look something like that. This is further up. So. Does that look a little better? Thank you for assuaging my ego. Yeah, these things are hard to actually draw, and don't worry, I'm never going to make you actually have to draw one of these yourself. I just want you to be able to sort of visualize what sort of thing you're finding the surface area of. So here's our point A, here's our point B, which kind of represent the top and bottom of our vase shape, if you rotate your head, however you want to think about it. Let's pick a point X here in the middle. So what would the area of the circle, or not area, I'm too used to thinking about the word area in this class. What would the circumference of the circle taken at X look like? Well, first of all, it may help us to just think in general. If we have a circle whose radius is r, what's going to be the circumference of that circle in terms of r? Nora? 2πr. Yeah, it's going to be 2 pi r. Or it's pi times the diameter, or 2 pi times the radius. And Kate, you mentioned 2 pi earlier. Here's where I think that 2 pi might come into play. So if we look at this circle right here, the circle taken by, we're taking f of x at some point x, and we're rotating around the x-axis 360 degrees, or 2 pi radians. What's going to be the radius of that circle? Okay.
F of X.
Yeah. If you look at what's the radius of this circle going to be right here? The radius is just going to be the distance from the center of the circle, which is on the x-axis. Here we go. To the top of the circle, So the radius, this distance right here, should just be equal to the distance from f of x to 0, which is f of x itself. So our overall formula then, Gabe, what's the overall formula going to be for the circumference of this circle in this picture drawn at the point x?
2 pi times f of x.
It's going to be 2 pi times f of x. And so then the idea for how do we find the surface area is we find the circumference of the circle at every single point x between A and B, and then we add them all together. And that should give us our surface area. Any questions or comments on that? All right, I've got a question then. How do we add together the circumferences of infinitely many circles? That sounds like a lot of work, trying to add together infinitely many circumferences. Jonah?
Sounds like a limit.
Sounds like a limit might be done. A limit as, say, n goes to infinity or something like that?
Very possibly.
Quite possibly. All right. Ugh, that sounds like a lot of work. Aiden?
Just integrate it.
Yeah, we can integrate it. I think that's, which in essence is taking a limit as n goes to infinity of a sum of n terms. But if you remember back to your Calc 1 days, the way we find the actual area under f of x is you have these infinitesimally skinny rectangles that you're adding up the areas of these infinitely many tiny, tiny rectangles. And that gives us the area under the curve. That if you take a limit as n goes to infinity of, say, I don't know, a right endpoint approximation r sub n, turns out we can find that from just integrating f of x from a to b, and then we can use fundamental theorem of calculus, as Gabe suggested earlier, in order to do that. So what we're going to be doing here, and this is going to be the formula that we're going to be using, is in order to find the surface area of this rotated shape, we're going to be integrating from x equals a to x equals b the circumference of circle taken at x from x equals a to x equals b. And we're also going to need to multiply that by the length of the curve. And if we can do that, then that's going to give us our formula for how we would compute the surface area of this strange base shape, for taking a curve and spinning it 360 degrees about the x-axis. Okay, well, as Gabe pointed out earlier, we know what the circumference of a single circle is going to be. Taken at x, that's just going to be 2 pi times f of x. How do we find the length of the curve, f of x, from a to b? We'll need to know kind of the length. In order to be able to apply this formula, we need to know what the length of that curve is, which sort of gives us a weird way of looking at the height of the cylinder if we were to take our cylinder and pull it out tight so that it ends up being a cylinder instead of whatever weird shape it currently is. I saw a couple hands a second ago and they seem to have gone down. Phoebe?
Use the arc length formula that we learned.
Yeah, here's where we need to plug in our arc length formula that we learned way back in Standard 8. Anybody remember what that formula was? Specifically, what function we had to integrate? Rowan?
Square root of 1 plus f prime of x squared.
Yeah. And so our final formula, the one that we're going to be going with, for finding the surface area of the shape we get from rotating our function around the x-axis from A to B, is going to be I'm going to pull 2 pi outside of the integral as just a constant multiple. So we'll get 2 pi times the integral from A to B of f of x times square root of 1 plus f prime of x squared. And that is going to be the formula that we're going to work with from here on out in the process. Any questions or comments about this formula? Where does it come from? So in practice, actually finding these sorts of surface areas, it ends up being pretty similar to the process we went through back in Standard 8 for looking at arc length, in that we have to integrate this thing, square root of 1 plus f prime of x squared. The only difference is when we're computing surface area, we also have to multiply by the function the original function f of x inside of our integral, and then multiply by 2 pi once we've actually integrated everything. So, okay, as you hypothesize, we do in fact have a 2 pi that kind of shows up as part of our expression. We end up with 2 pi times integral of blah-bitty bloopity blip. And the reason why 2 pi comes into play is the fact that our circumference formula, as Nora pointed out earlier, has a 2 pi that shows up in it. Circumference is 2 pi times radius. Or in this case, it's 2 pi times f of x. How are y'all doing? Y'all doing okay? Katie, you hanging in there? Just about. All right. So let's look at some specific examples. Now that we have a formula to work with, we can actually apply it and see what ends up happening when we try and look at a few different curves. So I'm going to be on page 2. All right, so anybody following the NCAA basketball tournament right now? So fun fact about me, I'm from Louisville, Kentucky, and as a loyal Kentuckian, we lost over the weekend, which was sad, but I'm required to follow college basketball along with horse racing as the state sport of choice. So one thing that they'll do at these sporting events, they don't really do them nowadays because we have modern technology. Back in the day, if you have someone out there who's announcing the game, they'll have this sort of megaphone that they speak into and it magnifies their voice. Let's start off by finding what's going to be the surface area of one of these megaphone type things. Just, as a kickback to the old days of sports. So let's start by looking at the function f of x equals x cubed, and we're going to rotate around the x-axis from x equals 0 to x equals 2. So f of x equals x cubed looks something like I don't know, looks something like that. And then it goes down to the left of x equals 0, but we don't really care about the left of 0 in this problem. So we're going to go from 0 to 2. And what we're going to do is we're going to take this shape and sort of rotate it about the x-axis. To get a shape that looks something like one of these megaphone shapes. I need one of these megaphones in my real analysis class because apparently they haven't fixed the airflow problem over spring break. So, how do I find the surface area? Well, we can use the formula that we just found in order to do that. So let's try that out. We're going to need to take 2 pi times the integral from x equals what to x equals what, Nathan?
From 0 to 2.
Yeah, 0 to 2. Those are the 2 x values that we're given. F of x times square root of 1 plus f prime of x quantity squared. Okay, well, we know what our f of x is. Our f of x is just going to be x cubed. What's going to be our f prime of x, Joanna? If f of x is x cubed.
3x squared.
Yeah, it'll be 3x squared using the power rule. So we get 1 plus 3x squared, quantity squared. Or in other words, 2 pi times the integral from 0 to 2 of x cubed square root of 1 plus, Kate, what would we get if we took 3x squared and then squared all of that?
9x to the 4th.
1 plus 9x to the 4th. So far, so good? I had a professor in grad school, my analysis professor, who literally, like, every time he wrote a line on the board would just say without looking back, ooh, so far so good. And then the next step we have, he just kind of says like, oh, okay. I'm glad you think it's so far so good. I'm stuck and don't know what's going on, but I'm glad you feel that way, Professor. How do we integrate this thing? X cubed times square root of 1 plus 9x to the 4th. Believe it or not, if this x cubed term wasn't here, this would actually be harder, in my opinion. Having this x cubed term here means that there's an integration technique that we could try out that's not quite so bad. Jonah?
You said?
Okay. Jonah wants to try out a u sub. Joe, what would you propose as a u then?
1 plus 9x to the 4th.
Okay. So if we do that, u equals 1 plus 9x to the 4th. What would our du be?
36x cubed.
36x cubed? Incorrect.
Dx.
Dx. Ah, now I like it. Okay. And then,
You like
oh, just a second. They have a question. Phoebe?
Could you also write the square root as like a power of 1/2?
I think we're going to do that in the next step. Yeah. Because eventually, or once we come back here, we're going to write square root of u. I think we're going to write u as that as u to the 1/2 and then use reverse power rule that when we are doing our actual integration. But yeah, I think that's a good call. Okay, so du is 36x cubed dx. I don't see a 36x cubed dx. I do see an x cubed dx. So I think du over 36, we can put that in place of our x cubed and dx term. So once we try and integrate, we'll get 2 pi integral from 0 to 2 of what? Square root of u times du over 36? So, Phoebe, you had an interesting suggestion, which is to take square root of u and just write that as u to the 1/2 power. I like that idea. What are we going to do with this oath dividing by 36? James?
You can just pull it out.
Yeah, that's a constant multiple, so we can just pull that out in front of the integral if we like, write it as 2 pi over 36, u to the 1/2 du. Swoosh, swoosh, this becomes just pi over 18. So how do we integrate u to the 1/2 power with, oh my goodness gracious, I just made a rookie mistake. Gotta remember 0 and 2 are x values, not u values. Ooh, that could have been catastrophic. How do we integrate u to the 1/2 power? You can tell I'm coming off a break as well. How do we integrate this? Bethany?
So we can write it as u to the 1/2, and then like we add 1 to the exponent, so that would become 3/2, and then divide it by 3/2.
Yeah, we get u to the 3/2 over 3/2. And then plus c, but since this is a definite integral, we don't need the plus c. From x equals 0 to x equals 2. Which becomes what? Pi over 18 times 2/3 times the quantity, what was our u? 1 plus 9x to the 4th to the 3/2. Evaluated from 0 to 2. And I see an opportunity for a little bit of swooshing. So we get pi over 27, my favorite number, times 1 plus 9x to the 4th, all to the 3/2 power, evaluated from 0 to 2. Joy, where would you go from here?
Could we just plug the values in?
Yeah, I think at this point, we just need to plug in 0 and 2 for x and subtract. Same as with any other definite integral that we had worked on. Okay, so if we plug in 2, we'll get pi over 27 times 1 plus 9 times, what's 2 to the 4th? 2, 4, 8, 16. To the 3/2 minus pi over 27 times 1 plus 9 times, well, 0 to the 4th, which is 0 to the 3/2. 16 times 9 is 90 plus 54, that's 144. Plus 1 is 145 to the 3/2 power. Minus pi over 27 times, well, 1 to the 3/2 power. All right, James, what's 145 to the 3/2 power?
A constant number.
Yeah, which one?
One of them.
One of them. Yeah. Fortunately, I don't think that's a nice number. If 145 was something we could take the square root of, then we could take its square root and then cube that. Well, its square root is something very slightly bigger than 12, since 12 squared is 144. Fortunately, that's not a nice number, so I think we're just going to leave that one like that. Alright, James, how about 1 to the 3/2 power? Is that one any easier?
Yeah, just 1.
That's just gonna be 1. Because 1 to any power is always gonna be 1. And I think that's gonna be our answer. Pi over 27 times 145 to the 3/2 power minus pi over 27. Which, when I plugged into a calculator earlier, gave me a number that was about 230. So there you have it. That's how we would compute this. The surface area of this megaphone shape. Or if you prefer, you could turn it on its head and think of it as being like a party hat or something. But the idea is, when we take our curve and spin it around the x-axis, what we're really doing is we're taking these infinitely many little circles from between x equals 0 and x equals 2, and we're adding up all of their circumferences in order to get the surface area of this thing. This is the sort of question that if you were a mega bullhorn, megahorn, whatever you want to call it, manufacturer, you would care a lot about. Like, hey, I want to make a bullhorn thing that looks like this. How much material am I going to need in order to make that happen? Or how much is it going to cost me to make a horn that that satisfies this properties, that looks like this? Knowing these sort of formulas for surface areas can be extremely useful in the real world. Any questions or comments? So really, that's all Standard 9 is. Well, until we get to some sneaky stuff on Wednesday. We're sort of applying this formula, this 2 pi integral from a to b of f of x squared of 1 plus f prime of x, and we're using it to compute various types of surface areas of general surfaces. And again, integrating something like this, we're not going to be using any new integration techniques. Doesn't mean we might not need some old integration techniques like U substitution, as Jonah suggested, in order to help us actually carry out our integration process, though. All right, y'all are looking antsy, so I'm going to give you all one to work on now. So if you all flip to the next page in the packet, I have another one for you to look at. This time I'm going to give you a lampshade. I'm going to give you all a curve from x equals 1 to x equals e. And what I want for you all to do is to tell me what's the surface area of this lampshade shape, where the function we're going to be integrating is the function that's going to give us our curve up here is h of x equals 1/4 x squared minus 1/2 natural log of x. And your goal is to find the surface area from rotating this about the x-axis from x equals 1 to x equals e. So go ahead, take a few minutes, and as always, flag me down if you have questions or talk to your neighbors and see what you can find from trying to look at this surface area right here. That's tragic. One big thing. This one's a little bit of a trickier example. So if you get stuck, definitely feel free to work with your classmates on this one. And as a hint, you should, when you get to the point where you're taking square root of 1 plus h prime of x squared, you should be able to simplify what's under the square root into something that is a perfect square. Some food for thought. What's up?
Probably just trying to put on the algebra and real big count ones, but this is one thing that you can measure,
Yeah, so when you differentiate natural log of x, you'll get x to the negative 1 or whatever x. Yeah, so that's how, yeah. So the stuff that's, so this stuff right here, that's what I got for my h prime of x.
Okay.
1 half x minus 1 half x to the negative 1 from differentiating h of x.
Okay.
And then you have to do some algebra to simplify what's under the square root, I think. Hey, what's that mean?
So from there, from underneath the square root, I can hear it, but I don't. Right.
Oh, let's stop. So let me grab my notes here. into that expression? Sure. The problem is, I think you got something different when you multiply this out than what I did. So when I multiply that out, I got 1/4 x squared minus 1/2 plus 1/4, well, x to the -2. Yeah. Yeah, did you foil it? I think you'll need to do, I would say, I think you'll need to do some foiling to multiply out the 1/2 x minus 1/2 x to the -1 quantity squared. Come on. Vern taught you a hack. What's that?
Dr. Crystal, I can't remember, can't you break this up into the integral of this expression times the integral of this expression?
That doesn't sound like how the product rule works to me.
Okay.
I think you can multiply all of that out
Okay.
and then try and integrate what's
Yeah.
left.
Yeah, I've just been trying to multiply all of it out.
To me, it helped to write this as just 1/2 x plus 1/2 x to the -1.
Okay.
And then you could just do some foiling to multiply that expression out.
Little wall.
You hit a wall?
Yeah.
I'll give you a hint. I do think you are going to have a 1/2 x. So you might ask, what term, when you multiply square it, is going to give you a plus 1 over 4x squared? Because that'll be the other term in your factors. And then the plus 1/2 will come from multiplying the a
1/2 x minus 1/2 x to the -1. Do that. I mean, like for the actual, the entire thing. Once you like. Okay, I got 1/4 x squared plus negative 1/2 x to the -1 plus 1/4 x. 1/4 times x. Oh wait, he is up there. Yeah, I didn't get that actually. Oh wait.
Now I like it. Took a second to convince myself of it. Oh my goodness, I'll give you a hint.
Like basic algebra is just like flying out.
And because plain and square is not something we've really done. So I wrote 'em. Answer me this: what term when we square it will give us a 1/4 x squared?
1/2x.
What term when we square it will give us a 1/4 x to the negative 2?
1/2x to the negative 1.
If we took 1/2 x times 1/2 x to the negative 1 and multiplied by 2, what would that give us?
Multiplied by 2.
Because technically if we were taking like a plus b quantity squared, we'll get a squared plus 2ab plus b squared.
So what are we multiplying by 2?
That times that. So the 2ab,
So 1/4 times 2.
Oh.
1/4 times 2 is 1/2.
Right.
I think that's what you would get.
So it's basically just the term that we had above.
It's not the term we have above, because we've gone from a minus to a plus when we added 1 to it. Technically, I think this should be a minus 1/2. Because you take 1/2 x times negative 1/2 x to negative. When you square this out, you get a minus 1/4 minus 1/4 becomes minus 1/2 right here. And then I took the 1 minus 1/2 to get positive 1/2. I combined this one and this negative 1/2. Does that make sense?
Yes.
Cool. Hey, what's up, kid?
Because the
That
square
also
root
works.
and the square root.
Yeah, because if you simplify this, you get x squared over 2x, which is just 1/2 x, plus 1 over 2x, which is plus 1/2 x to negative 1.
But I'm like,
Oh, yeah.
it's not.
Yep. Yeah, then you just FOIL these out and it ends up with several things, none of which are individually all that bad.
Okay.
Hey Lauren, what's up?
And then like, I don't know if that should I.
You're taking square root of things squared. How does the square root and squaring interact with each other? Yeah, so I would cancel out this square root and this squaring right here. So you're left with 1/4 x squared minus 1/2 natural log of x times 1/2 x plus 1/2 x to negative 1. I would FOIL that out and then see how you would integrate the corresponding expression of the FOIL. Yes, technically you have big parentheses around there, here and here, and then you can do some FOIL on that to give you some stuff that we can actually integrate. Does that sound good? Cool. This one's a bit more in depth than the first problem for sure. Just so we're clear, if I were to ask you a quiz question on the standard, it would be more like the x cubed problem and less like this one. But I thought it would be fun for you all to try this one. You having fun, Dev?
No. Not anymore. I know how many babysitters feel.
Stop clubbing the big C's.
So this
I multiplied HX
So
by
now you're left with
and
this.
then I just opened up this one.
Yeah, so then now I'm just like these. Yeah.
If that's a fair game in the math world.
If what's fair game in the math world?
Did you get this?
You could, yeah, if you have a sum of 4 different terms, you can always integrate each piece separately. I'm sorry? You're just thinking through this.
It's just X over 8.
Meaning me?
No.
Meaning meaning the shadowy police force we have hiding in our department.
I knew it.
I don't like this.
Notice how there's a couple students who started the semester with us and are no longer here.
It's Big Hillsdale, man. I keep telling people that this is real.
Just making an observation.
Big Hillsdale.
Beginning of the semester, every one of these seats was filled.
So,
They're not. There's one behind Ty. There's one behind Rodham that are not.
no, that's true.
But now because you.
But everybody needs a cut.
This one, can you multiply the top and
Oh,
bottom
you know
by
what I'm
X?
thinking?
Hide the shade, you can't do it, just so around it.
Oh, wait.
I think it might be two right here. Because these two are
And then it's easier.
Easier.
these two are things that we've seen before and know how to handle, but are going to also Oh, we're not gonna finish it in class today. We're gonna talk about it in class Wednesday.
Maybe just at the, I know, I think she's like the end.
Hey, what's up?
Like break these up, so we make it into every part. Does that mean I have to multiply 2 pi by every part as well?
You could just integrate each piece separately, and if you want to, you can ignore the 2 pi up until the very end. Just integrate from 1 to e, and then just multiply your final answer by 2 pi if you want. So you'll get stuff, and then you'll multiply by 2 pi. Oh no, that's so hard.
Too many parts.
Too many parts.
It's too early in the morning for this.
I mean, you signed up for a 7:45.
You were the one that made it at 7:45.
I was the one who made it at
This is
7:45.
This is taking up my entire
This
page.
is giving 1 o'clock class.
Say what?
This is giving 1 o'clock class.
No, because then I'd be asleep after lunch.
I was gonna say, there's a competition section at 2 o'clock that you don't have to sign up for, but.
Did you simplify this out to X over E?
Yeah. Yep.
Okay. Oh god.
Yeah, that's what I was thinking.
What's the word?
That sounds right. I just think in order to integrate this piece, you might need to do some,
I know.
use some of our more advanced techniques.
It's like, this problem also
Well, that's why, I thought this made for good practice problem, because you have to do so many different things, and it's a reminder of so many different techniques.
It does, and it is, it just,
And
it's a
that
big
makes it
wake up
painful.
call. It just is a big wake up call to remind everyone.
I know. I needed to get y'all back in the swing of things somehow.
I know, exactly. First, you should have given us more.
How else by terrorizing them?
Yeah.
I'm beginning to rethink my stance about being, so every now and then, okay, with certain war crimes.
One of them is a
I see. Glad I can make you reflect upon your
You said you did
life
break
feeds.
these separately.
But I, like, if you were to take this as a new cell,
How are you doing, Mary?
this is a minus.
It's going okay?
This is a minus and this is
Sure you guys.
I don't think it would cancel itself out.
That looks very scary. So, I'll give you a hint. So what I did here is I actually FOILed this out, and then you get 4 terms that you can just integrate each one separately. Might make your life a little bit easier. Yes, Jonah?
I was like, no, it doesn't. Or it does, but it doesn't.
Oh, okay. What's up, Mark? Oh, you look like you were gonna ask me something, like you're situating yourself to.
No. I'm trying to figure out, did you like everything in, or I guess.
Well, we'll talk about that. So we'll finish this problem in Wednesday's class, after the quiz, also in Wednesday's class. Gabe's gonna come play the horn for us finally in class, so that'll be fun. Right, Gabe?
Yeah.
Alright, so with that, hope you all have a good one, and I'll see you all from Wednesday where we'll do our standard 8 quiz and continue our discussion of these surface areas.
I was go home, Caroline's like, yeah, so